This video is for P2 and it's on atoms and radioactivity. Comes up in P2 Part 2 AQA. So last year there was a massive question on the plum pudding and Rutherford's experiment. So whether it will come up again, I don't know, but you never know. You do need to know about the atom, and it isn't just chemistry. That came up as a 6 marker last year, which was really, really nice. You need to know about the neutrons and the protons being in the centre of the nucleus, the fact that protons have a positive charge and a mass of 1, neutrons have a neutral charge and a mass of 1, and electrons have a negligible mass. Sorry, they don't have no mass, they do have mass, but it's so small we can't really measure it. It equates to about 1/2000 compared to a neutron or a proton, and they orbit in shells. Overall charge of a atom is neutral because it's got the same number of protons as electrons. If you lose electrons, you become a positive ion. If you gain electrons, you become a negative ion. An isotope, though, is something with the same number of protons, because that's what makes it that atom, but it has different numbers of neutrons, so it's got different physical properties but the same chemical properties. It would still react the same. Plum pudding, okay? Last year they asked you about what the pudding represented. Now, the pudding is positive. Everyone loves pudding. Of course it's positive. Raisins, not so much. I'm not a fan. So to me, raisins are quite negative. It then asked you about Rutherford's experiment with the gold leaf. Basically, alpha particles, which have a relatively large charge of +2, are fired at gold leaf, which is like 1 atom thin. Some of the alpha particles are repelled and scattered, which proves that it had a positive nucleus. But whether that come up again, I just don't know. Radioactivity, though, hasn't been on in a while in terms of background radiation. Now, 85.7% of our background radiation is from natural occurrences, nothing to do with us. Only 14.3% are artificial from our doing. So we have rocks, radon gas inside rocks. You have ground and buildings because it's made from rocks. You have food and drink because it comes from rocks. And then you have CMBR, or cosmic microwave background radiation, which is about 10% of our background radiation. Medical-wise, it's actually 14% for medical, I know. Weapons testing and things is 0.2, and things like the Chernobyl disaster and stuff like that is only 0.1, so nuclear accidents. So it hasn't actually contributed to that much. Might ask you about the exposure rate, okay? So things like air crew, because they're in the sky, they're exposed to CMBR, are quite exposed. Radiographers are working with it. Now, I know they go behind screens to be safe, but then they go out and they meet the patient that they've just ionized, basically. So that's it. Security, miners. Things like people who work in nuclear power stations and stuff actually are really well protected, so they're quite low on the scale. Things like a physics teacher like me, I might get radioactives out about 4 times a year, so then I'm exposed as well. Now, radioactive decay is actually a random process, and atoms will do this, or isotopes, so they become more stable at a lower energy level, so that's when they'll fire out the different types of radiation. Half-life came up last year, but working it out from some text, not from a graph. So this is a half-life graph. Now, half-life is basically the average time it takes for half the radioactive nuclei, to decay, or the time it takes to get to half of its activity rate. Okay, either is acceptable. So you just go to the graph, say it was 2000, go down to 1000 because it's half, read across, and then just go down. So this one, for example, was 10 years. So then it would be another 10 years on top of that to get to 500, another 10 years on top of that to get to 250. So you just halve it and half it, okay? That's why it kind of goes down and it never really gets to 0. There is a video on that too. I'll go over this way first. So we have the 3 different types of radiation. These didn't come up last year a lot. They asked you about fission, fusion, but not specifically about these. Alpha particles, we say, are the same as a helium nucleus. It's made up of 2 protons and 2 neutrons. So if you were putting it like you would a normal atom in a periodic table, it has a mass of 4 and an atomic number of 2. So say uranium-238 were to release alpha, you would put this number 92 down by 2, it become 90, and this number 238 down by 4, so it become 234. And you'd have also an alpha particle. If you were to add this back onto it, conservation of mass and all that, you'd get back to this original, okay? Alpha is the most ionizing. Now, this is because ionization is when you knock electrons off of atoms to make them an ion. Now, the size of 2 protons and 2 neutrons is quite big compared to the size of a little tiny electron. That's why we say it's the most ionizing. It has the most chance of knocking electrons off of cells. That said, though, it gets stopped by skin and paper, and it can only travel a couple of centimetres in air, so it's nothing to worry about too much. Beta radiation is a fast-moving electron, okay? It has no mass change, and this is -1. Now, it happens when a neutron will randomly change into a proton and it emits an electron. So because this happens, the atomic number of the substance actually increases by 1. So again, if we had uranium-92 238 and it released beta radiation, it would then increase by 1 for the atomic number, but the mass number would remain unchanged. Again, if you're looking at this, if you added this -1 onto 93, you would get 92, and if you added 0 onto 238, you still get 238. So that's a way to remember it. Beta gets stopped by millimetres of aluminium. It can travel quite a distance in air, but again, it's an electron knocking off an electron, so it's less ionising than alpha, because what are the chances of that happening? Gamma radiation is an electromagnetic wave. It has a high frequency. It doesn't have a mass, okay? So if it was released, nothing would change. It generally releases this at the same time it releases alpha or beta, just to get to a lower energy level. It can travel really, really far from some space. It gets stopped by, though, centimetres of lead or metres of concrete, which is why we encase Chernobyl in metres of concrete. Uses of these hasn't come up in a while. Alpha radiation can be used to ionise air within a smoke detector. So the way it works is you have a source and then you have a gap between a circuit. The alpha radiation will ionise the air, so it'll knock electrons off the air, and these electrons will then complete a circuit and the alarm won't go off. As soon as smoke gets in there, there's too much smoke to actually ionise, so the detector will go off. Beta can be used in paper mills or even aluminium factories. They have a beta source, it fires it through to a detector, which will have a set number that it needs to be at. If this number gets too low, that means the paper's got too thick, so the automatic rollers will then cause it to squeeze together. If the number gets too high, it means the paper's too thin, so it will separate the rollers again. Gamma radiation can be used in medical tracers, or also can be used to treat targeted tumours. The way it would work, it would rotate around the tumour so that the cross-section where the tumour is gains the most gamma radiation, but the healthy cells would get the least radiation. All these radiations are ionising, okay? And if you're asking what's the danger of ionisation, ionisation can lead to cancer. It can make your cells mutate, and then that could lead to cancer. Fission is the splitting of large nuclei into smaller nuclei. Don't say atom. Nuclear fission is all about the nucleus, okay? And that's using things like power stations. Nuclear fusion, though, is when smaller nuclei fuse to make larger nuclei, and that occurs in stars like our sun. The star life cycle. Now, there is a video on this one as well if you want to get more detail. I have a feeling it might be the 6 marker. I don't know. Recent years have asked about this strand, but not this strand. So you have a cloud of dust and gas, which is a nebula. That comes together under gravity to form a protostar. Eventually that switches on and it becomes, nuclear fusion happens and it gets into its main sequence. It's in about this stage, about 90% of its life. Now, average sized stars or smaller, like our sun, go this direction. So a red giant will fuse up to oxygen. That will eventually, from a planetary nebula, its outer atmosphere will go off into space, and it will leave a core of a white dwarf. Then over millions of years, this cools down to become a black dwarf. Stars much more massive than our sun, and they do get more massive than our sun, however, would form a red supergiant. Now, these can form up to iron. Once they've got an iron core, they can't do any more nuclear fusion. So what happens is the core collapses in itself, ricochets off the core, and you get a supernova explosion. Now, this is where heavier elements than iron, things like platinum rings, girls, are formed in supernovas. So any metal you've got on you that's heavier than iron formed in a supernova. That's pretty fantastic, I think. This can go one of two ways. So it can either, if it's quite big but not that big, it'll become a neutron star which spins around and gives out radio waves, or it could become a black hole, which we all know that not even light can escape from a black hole. So I really do need to focus on this, guys, and this, and this I would focus on as well. Thank you.